Okay, I move to what about the portions of signal is feedback in PID control is here is a proportional is called the gain P is like a constant. But in the integration is the I is integrate of the signal error here. Maybe Ki multiply. And this one is a KD multiplied with differentiation of the error here. So in the PID, we have KP plus KI integration EDT plus KD dE by dt.
อาจารย์ครับ don't share your screen right
Oh,
now.
sorry. Oh, okay. I just don't share, right?
Yep, can
Oh,
see now.
just don't share, right? Not for a long time, right?
Yeah. For a while, yeah.
Just, okay, sorry. You use cloud now?
Okay, now it's okay.
Okay. Okay. I told you about PID. What the meaning? P is a constant gain, like a proportional is mean constant, and I is mean integral of the signal, and D is mean differentiate of the signal. So PID is mean KP plus KI multiply integrations plus KD multiply differentiations. So I will show you why it's very popular and still used 95% at now of PID. Okay, and first now you can know about PID stand for. Even PID is published on here 1922, and PID concern originate from now. But okay, now they use in the industry, and more than 95% of closed loop industry process they're controlling by PID. So that's why we can say very super good controller structure. And what is about PID controller? Like you see here, the negative feedback. The controller C is here. So if the controller C is a KP constant, it's called P control. This is called P controller. But it have some value divided by S. You know 1 over S is the integral in Laplace. S is mean differentiate in Laplace, you know? You familiar with this one? If you see the integral here, you say it is a PI control. If you say differentiate here, but you have some another bit filter, we're talking about this one later, why we have this one. This one is a PD control. But if you have both part I and D, you still have PID control. So many cases you just use only PI enough. Some cases you use PD enough. In some cases you use PID. But this form is also PID. Okay, there are many forms of PID, so I will talking about this one later. And okay, again, it's called PID. Is a control error method, and they have the form P, PI, PD, and PID. They have many forms, and all we can say it is those are PID. And okay, more than 95% in the world they use PID. And this is their structure in the control law. They have the proportional, integral, and differential for this one. Okay, and this is the Laplace form of this one. You see, integral is a 1 over S. Differential is a S here. Okay, now I told you about why proportionals now, but I would like you to say about why integral. Why integrals? Okay. I talking about some models. some very old motor. If you put voltage to the motor, they control the speed here. If you put high voltage, you got high speed. But um, imagine everything in the world have dead zone or backlash. I'm not sure you're familiar with two words here. Dead zone or backlash. What does it mean? Imagine I have one motor. I put 1 volt to the motor, the speed is 0. I put 2 volt to the motor, the speed is 0. I put 10 volt to the motor, the speed is a 0. But when I put 11 volt, the speed coming to 20 RPM, for example. If I put 20 volt there, it comes with 40 RPM, for example. You have familiar with this action or not? Okay, I ask someone, you have familiar with this action or not? Like a old motor, fan motors. Noptagon. Have you familiar with this phenomena, right? With this symptom of your old fan?
Yes, if we example the electrical fan,
Yes.
yeah,
Sometimes you put gear number 1, they don't move. And you
yeah,
use your hand to move it, they run faster, right?
yes.
Yes, why
It's like uh, to initiate from start to the expect
Yep, yep.
target.
Even
It
in the
takes
old,
some time.
old electric fan, right? But the new one is not, right?
Yes,
Even in the especially in the old electric fan, you can have familiar like this. Okay, you have a fan here. You put gear number 1, they don't move. You use your hand to tell them if they move. Okay, because everyone in the mechanics, they have something like this. First
it's
is mean static and dynamic frictions. Okay, this is the velocity, this is the frictions. The motor have to have the torque higher than the friction, then start to move. So in many cases, you look like this. Okay, if your velocity is low, it's become high frictions. If your velocity is fast, it's a lower frictions. I have some example of a truck for very big car. Okay, very big car. You use one people to support you to push it, but it's not move. So you call your friends, maybe 10 people, push the car here. They're starting to move because your force is high enough to making some more than friction at starting static frictions. Then the car move a little bit. Your nine friends go out. You still have alone again, so you can move a car now. Even you don't have your friends, but your friend help you at the starting. Are you okay? What I say? If you understand me, let's see this one. In the controller, you say the error, the KP multiply error go to the force to the system U. So if error lower, so the U is lower. Like as someone said to me, if the error becomes 0, you no need to push anything to the system. They go to the target already, right? But okay, unfortunately, when you go to the target, what happened? You see, when you go to the target, and this one at this point, the error becomes low, very low. Your U or put to the system is very low as well. Okay, it makes sense that if you have low error, you should put U very low. It's really makes sense. But unfortunately, when your system go to slower speed, the system is not linear. They have some friction. So if they have some friction, sometimes your system stopped at this point because your KP error, if you have only proportional control, U is KP error, so it's not enough to win or to more than friction. You understand me? Okay, how to solve these problems? Some people said, okay, you put very high KP. What happens if you put very high KP? Your order, you may go like this, oscillate, because too high of controller. Your error is here, you put very much, okay? So some idea is that if you have error for a time, that means you deal with the friction like this. You integrate error here. For example, if error is a 0.1 meter, you come to the next feedback is a 0.2, is a cumulative of the error. If this cumulative of the error have more than the frictions, they will compensate. This one go here. That's why the integral is very, very important as well to deal with these friction phenomena that occur in many mechanical systems. So you can see many mechanical systems, they use PI control, but many electrical systems, they use only PD. I will show you why PD the next. Okay, are you okay what I say?
Okay, Ajan.
Okay, if you understand why I will show you why D, why differentiation. So let's say if I accelerate the system too much, it's become like this, you hear? So you don't want oscillation here. Okay, this is error, this is times. Okay, why I say you have this one is a command R, this one is a Y, this is Y. So the error become here. R minus Y, this is R minus Y is error, become here. I ask you one questions. How can I know that my system is oscillate? How can I know? If you don't want oscillation like this, how can I know that our system is oscillate? Which parameter indicated the system oscillate? You know, slope of graph. If the system is here, you think it's oscillate or not? No, because at this point, the slope become look like zero, right? Slope. It does not have many slopes. But if the slope is here, you see, the indicate of oscillation is slope of the graph in these situations. The slope is mean differential. So you can say dE by dt is the slope. If you capture the slope and you again the slope by kd, so your controller will damp this one to, for example, before adding d like this, after adding d become like this. That means I can damp the oscillation in the response on the response. So now I think I talking about why PID is very popular. Hopefully you understand. And in my conclusions, before I start to deeply detail in the PID, I show you here. This is the PID table. If you have the response and this response very slow, you want to faster, decrease lifetime is mean faster, very faster. You put PID higher. And if you would like to eliminate steady state error, you put KI. And if you would like to decrease the overshoot or oscillate, you making higher KD. In conclusion, KI make the system faster, KP zero error at steady state, and KD to KP, sorry, KD here is a damp the oscillation. Okay, you can have rule of thumb here. Even you have 3 rules, you can tune the controller everything in the world. Enough. Okay, are you okay now? Do you have any questions with my teaching today? I'm not finished, but I will go through the Scilab program.